Current. Electric current is the rate at which charge flows. The letter I is the symbol for current. Capital I current equals amount of charge divided by amount of time. So let's say you were sitting next to a wire and you were counting all the charges that were flowing past, and you were calculating how much charge was passing by this particular location in a certain amount of time. Current has the units coulombs per second, since charge is measured in coulombs and time is measured in seconds. The units can be rewritten as amperes, so that's a special name for coulombs per second. 1 amp, or ampere, equals 1 coulomb per second. Note, current is not the speed at which charges are flowing. It is the amount of charge that is passing through a location per second. We know that if an electric potential difference is applied to a wire, charges will flow from high to low potential. However, due to a convention set by Benjamin Franklin, current in a wire is defined as the movement of positive charges and is called conventional current. Positive charges are imagined to move in the direction of the electric field, leaving the positive end of a battery and re-entering the negative end. In reality, in most circuits with copper wires, for example, it's electrons that are moving, and they move in the opposite direction to conventional current. Electrons are actually leaving the negative end, going around and entering the positive end. A good analogy to help understand electric current is to consider water flow. The flow of water molecules in a river is similar to the flow of charges in a wire. The water current depends on the pressure exerted on the molecules, either by a pump or by a height difference, such as water falling off a cliff. Electric current depends on the pressure exerted by the electric potential difference. The greater the electric potential difference, the greater the electric current. In a circuit, a battery is one way to provide a constant electric potential difference. Here, there's no electric potential difference. That's like a lake of charges. They move around in random directions, but not all in one direction. So there's zero current. Here, an electric potential difference is like a height difference, so the current will flow downhill. Batteries with different voltages will provide different electric potential differences. A 9-volt battery has an electric potential difference of 9 volts, which raises charges up to a height of 9 volts. A 9-volt battery will create a steeper hill than a 1.5-volt battery. The steepness of the incline represents the strength of the electric field. Each battery has 2 terminals, which are conductors. The terminals are used to connect an external circuit, allowing the movement of charge. Batteries convert chemical energy to electrical energy, which maintains a constant potential difference. The chemical reaction acts like an escalator, carrying charge up to a higher voltage. What is the magnitude of the electric current passing through the heating coil of a hot plate if 36 coulombs of charge passes through it in 9 seconds? Well, current is the amount of charge in the amount of time, so that would be 36 coulombs in 9 seconds. That is 4 amps of current. And here is our solution. A current of 0.6 amps flows through a resistor. How much electric charge would flow through it in 3 minutes? All right, so we have a current of 0.6 amps. We have a time of 3 minutes, but we have to convert this to seconds. So let's just do that right away. Seconds, so 60 seconds in 1 minute gives us 180 seconds. Now, our equation is I equals delta Q over delta T. Therefore, delta Q equals the current times the amount of time. So that would be 0.6 amps times 180 seconds, and our solution is 108 coulombs. How long would it take for 250 coulombs of electric charge to pass through an aluminum wire
if the current through it is 0.5 amps. All right, so we're looking for the amount of time. We are given that the amount of charge is 250 coulombs and the current is 0.5 amps. So we start with our equation for current and we're going to solve it for time. So we're going to cross multiply, so we get I times delta T equals delta Q. We're going to divide both sides by I, and we get that the amount of time equals the amount of charge divided by the current. So that would be 250 coulombs divided by 0.5 amps, and our answer is, dividing by 0.5 is the same thing as multiplying by 2. Our answer is 500 seconds.